Welcome to Lesson 4, Smart Prosthetics and Assistive Technologies. This lesson explores how digital innovation is revolutionizing the field of rehabilitation and support for individuals with disabilities. We will move beyond traditional devices to understand how intelligent design, advanced materials, and seamless integration with human physiology are not just restoring function, but truly augmenting human capability. As biomedical engineers, you'll see how your skills directly impact quality of life, and as healthcare professionals, you'll learn how to leverage these technologies for patient benefit. Let's delve into this inspiring frontier of digital health. By the end of this lesson, you will be able to define both smart prosthetics and various assistive technologies. We will delve into the key components and sophisticated mechanisms that enable smart prosthetics to function. You'll explore a range of assistive technologies and their diverse applications, from mobility to communication. A crucial objective is to understand how digital integration, particularly through AI and advanced sensors, enhances the functionality and responsiveness of these devices. Finally, we'll discuss the profound impact these technologies have on human capability and quality of life, alongside the inherent challenges in their development and adoption. Let's begin with smart prosthetics. These are not merely passive cosmetic or mechanical replacements for lost limbs. Instead, they represent a leap forward, incorporating advanced robotics, sophisticated sensors, artificial intelligence, and intricate control systems. The primary aim of smart prosthetics is to restore lost function in a way that closely mimics natural limb movement and, increasingly, these devices often feature myoelectric control, where they interpret electrical signals generated by residual muscles in the limb stump to control the prosthetic's movements. They also include force and torque sensors to provide feedback on how the prosthetic is interacting with its environment. Robotic motors or actuators power their movements, all governed by embedded microprocessors and AI that learn and adapt to the user's intentions and environment. Some cutting-edge prosthetics even include haptic feedback systems to provide simulated sensations, further integrating the device with the user's body. The primary aim of smart prosthetics is to improve the quality of life for individuals with limb loss by restoring, or in some cases enhancing, natural mobility, functionality, and independence through advanced technology. These devices often feature myoelectric control, where they interpret electrical signals generated by residual muscles in the limb stump to control the prosthetic's movements. They also include force and torque sensors to provide feedback on how the prosthetic is interacting with its environment. Robotic motors or actuators power their movements, all governed by embedded microprocessors and AI that learn and adapt to the user's intentions and environment. Some cutting-edge prosthetics even include haptic feedback systems to provide simulated sensations, further integrating the device with the user's body. Moving beyond prosthetics, we have the broader category of assistive technologies. Assistive technologies encompass any device, software, or piece of equipment designed to help individuals with disabilities maintain, improve, or regain their functional capabilities, thereby enhancing their independence and quality of life. These technologies are truly transformative. Examples include smart wheelchairs equipped with obstacle avoidance and advanced navigation. Powered exoskeletons, or exosuits, provide mobility assistance for individuals with paralysis aids like eye-tracking devices or advanced speech-generating devices enable non-verbal individuals to communicate effectively. We also see smart home integration designed for accessibility, and sensory aids like smart canes that provide enhanced environmental awareness for the visually impaired. Let's pause for a quick check. Myoelectric control in smart prosthetics involves using brain signals directly to move the limb. True or false? The smart in smart prosthetics and assistive technologies comes directly from sophisticated digital integration, particularly through advanced sensors and artificial intelligence. Advanced sensors are crucial. Inertial measurement units, or IMUs, which combine accelerometers and gyroscopes, provide precise tracking of limb position and movement. Force and pressure sensors embedded in prosthetic feet or hands provide critical feedback on grip strength, ground reaction forces, and balance. Electromyography, or EMG sensors, are fundamental for myoelectric control, detecting the electrical signals from muscle contractions. And for assistive technologies like smart wheelchairs, environmental sensors are key for obstacle detection and safe navigation. All this rich sensor data is then processed by artificial intelligence and machine learning algorithms. AI excels at pattern recognition, interpreting complex sensor inputs and muscle signals to enable intuitive and natural control of the device. AI also provides adaptive control, allowing the devices to learn and optimize based on the user's unique gait patterns or intentions over time. In assistive technologies, AI can offer decision support, helping systems navigate complex environments more effectively. The impact of smart prosthetics and assistive technologies on an individual's quality of life is truly profound. They offer greatly increased mobility and independence, not just restoring movement but enabling greater self-reliance in daily tasks. This often leads to enhanced social inclusion, allowing individuals to participate more fully in social activities and reducing the stigma sometimes associated with disability. Crucially, these technologies can significantly improve mental health, boosting self-esteem and reducing feelings of isolation by enabling greater participation in life. They open up new vocational opportunities, allowing individuals to return to work or embark on new careers. For families and caregivers, greater independence for the user translates to a reduced caregiver burden. And a key advantage of smart technologies is their capacity for personalized adaptation, where devices can be continuously tailored and refined over time to perfectly match an individual's evolving needs and motor skills. Despite their immense potential, smart prosthetics and assistive technologies face significant challenges in both their development and widespread adoption. Firstly, their high cost of development and manufacturing limits accessibility for many who could benefit. Secondly, individual customization is paramount. Each user is unique, requiring precise fitting, calibration, and programming of the device, which is a labor-intensive process. User training and adaptation are also critical and often time-consuming. Learning to intuitively control an advanced prosthetic or exoskeleton can be a long journey. Battery life is a constant concern, as powering sophisticated electronics and robotic motors demands significant durability and maintenance are also key, as these devices need to withstand daily wear and tear and often require specialized, periodic maintenance. Beyond the technical, there are profound ethical considerations regarding human identity, the concept of augmentation, ensuring equitable access, and managing the privacy of highly personal data. Finally, navigating regulatory pathways to ensure the safety and efficacy of these highly complex and often integrated devices is a continuous challenge. Another quick check. Smart prosthetics are designed to fully replicate human skin sensation through integrated touch sensors. True or false? To conclude Lesson 4, we've explored how smart prosthetics utilize robotics, sensors, and AI to not just restore but genuinely augment the function of lost limbs. We've also seen that assistive technologies form a broader category, enhancing the functional capabilities of individuals across diverse needs. Digital integration, particularly through advanced sensors and artificial intelligence, is absolutely crucial for enabling intuitive control and adaptive behavior in these devices. The impact on quality of life is profound, leading to increased mobility, independence, and social inclusion. However, significant challenges persist, including high costs, the need for individual customization, extensive user training, and complex ethical considerations. As biomedical engineers, you are at the forefront of this inspiring field, bridging advanced engineering with the deeply human need for enhanced capability and improved life. We've reached the end of our first lesson. Now it's time to test your understanding with a graded quiz. This quiz consists of between 10 multiple-choice questions. Please choose the best answer for each question. You will have 10 minutes to complete the quiz. Remember, your score on this quiz will contribute to your overall course grade. Please take your time, review the concepts we've covered, and good luck.